permission. In my case, I have to do it 3 times. So I believe we are now being recorded, not that I ever intend to watch it again. I thought what we might do this morning is a couple of things. One, let me just show you, you can of course see me, which is always a pleasure. What we can do, for example, is the following. I've written some things down here and I can, it's like a tablet. It's not a tablet, it's actually a camera on a flat surface, but I can do some stuff. We can answer questions or write stuff out this way live, or if I stop that, for example, and somebody wants to come in. Can you guys see the ones that want to come in?
No.
Can you see on your screen, like on my screen, it says so-and-so wants to be admitted? Can you see that at all?
No,
We
it must be the
cannot.
host.
Okay, so I'll have to keep an eye, or you might remind me every once in a while, look and see if anybody else is in the waiting room. Anyway, if I go to the other screen here, what you now should see is something that's not familiar to you, but is sort of familiar to you. This is WebAssign. And what I have on the screen right now is what I can see. I've blanked your names and stuff, but your names are actually over here. But what I can see here, for example, if I take this person, they have spent so far in WebAssign 548 minutes. They, on the first assignment, they have 161 points, in the second assignment, and so on. This particular individual and all of these people with NDs have not, except for this 101, have not looked at section 3 at all. If we look at this individual, you'll notice they have been working all 5. And this individual down here has done all 5. Now, this person looked at this NSS. This NS means they opened up section 5 and looked at it, but didn't do anything. But they've spent 380 minutes so far, have 104 on the first thing, and so on. Okay, so I've got all of you here. I'm not interested in who's who. I just wanted to show you. And what I can do is go into each section and see exactly which questions you answered and which ones you did right and wrong. I don't have time to do all that stuff, but you can do a lot of, you can do a lot of things here if I want to. The reason I have this is to, and I'll have to sort of go over here and disguise things a minute. Let's go back home here. And now your names are not there. This is the screen that I see when I turn on WebAssign. These are the 5 sections. It's similar, I suppose, to yours. You can see over here on the left that I have 26 people that say they're students. Only as far as that roster goes, there's only 20 people who actually are registered. But anyway, if I go to this, hopefully, didn't seem to work, so let me try it again. Okay, here's a section. This is the thing that some of you guys want me to change right here, which I can change if I want to. Just you can't, but I can. And these are the things I thought we might later look at section 3. And so we can come back to this. Right now, I'm kind of only trying to show you what we can do at home, but we can't very well do at school. Like, we could even watch the video here if we wanted to. This, by the way, is the author who died. Nice guy. He used to write me and correspond with me occasionally. But we'll stop that share and you get to see my ugly persona here. So what do you think? You think if we ever have to do this again, or if we choose to do this again, is this a good format?
I think so.
Yeah, I think so too.
Looks fine to me.
I agree.
So we may have to decide. I don't know what the school is going to do tomorrow, but we may want to decide to do this anyway tomorrow, just because it's not going to be, the snow is not going to be gone tomorrow. But we can talk about that a little bit later. And also, how many people here? I only have 3, 6, 7 of you, so that's less than a third of the class. Okay, well, I thought, again, this can be your day, because I tried to say we can have it be a tutoring session and stuff, but I want to show you something first with your permission, or well, without your permission. All you can do is leave. And those of you who don't know me know I joke a lot. It's not funny, but that's, the way it goes. Okay, I thought I would talk a little bit about the matrix stuff and give you a little more insight about stuff. And I wrote this down, half hour ago, because I thought we could quickly do some stuff and then not spend much time on it. But the people who can't be here, we can do this kind of thing tomorrow if we're in class. Anyway, wanted to show you, it's a 3x3 screen, matrix, determinant of it. And yesterday we wrote it out. So I hope you see, and I emphasize the minus. And what you do to get to things, if you're doing this second one, for example, you wipe out the row and column it's in, and the 4 things that are left is what you put here. And I hope it's not blurred and stuff. Sometimes the camera doesn't show things distinctly. Anyway, in this particular case, I've got my finger on the wrong one. It would be on this one. And you can see these 4, I hope, and the 4 I have over here, but you put a minus. Now, to keep yourself straight, in case we have a lot more than 3x3, if we had 10x10 or whatever, if you can, as it turns out, we could prove, we are not going to, but we could prove that we could expand on the 3rd row instead of the 1st row. What does that mean? That means I could have A3, 1 here, and 3, 2, and 3, 3 here instead. And of course, if I did that, if I did A3, 1, then I would be wiping out these, and the 4 you see remaining here are also, would be the 4 that would occur here. Everybody kind of understand what I'm just copying. I mean, this is wrong, but I'm be copying those 4 things right here. And then when you take this determinant, this is just these 2 multiplied together minus those 2 multiplied together. That gives you 2 terms here, 2 here, and 2 here. And the thing that people make mistakes on is you have to have a minus here, if you're going to do it this way, blocking these things out horizontally and vertically up here. Okay, so that's the definition. As I say, one can prove that we could do the same thing, get the same answer. And the reason, by the way, if we wrote out these 6 things and did another one, like go down this column and wrote out those 6 things, you'd see that you get exactly the same 6 things. And for a 3x3 matrix, you actually could do all 6 of these computations and see that no matter which row or which column you do, it comes out the same. Now, if we had a 100 by 100 thing, you couldn't physically do that. So we actually can prove without worrying about how many it is. We just say there's n rows and n columns, and n could be 1,000,000. We can actually prove that each way you go will give you the same answer. If I expand by the 2nd row, even if it's 1,000,000 things long, it's the same as expanding by the 2nd column or the 1st row or the 100th column or the 1,000th column. So for 3x3, which is what we're going to be worried about, you can actually do it and show it, but we're just going to assume it right now. And so what I did here next is, instead of double subscripts, I used a single subscript, because what I want to talk about is cross product of 2 vectors. So we have a vector in 3, another vector in 3. Technically, I suppose I should be making these things like this temporarily. We want to define what we mean by cross product. Now, the actual definition is the one that is above my fingers here. It's A23 minus A3, A32B3 minus A3B2. These things, so I take this, the third thing here and multiply it to the second thing here, and I take, and so on. And so the answer to a cross product is a vector. It's got 3 components. And they're kind of complicated. So somebody decided, hey, why don't we, since these things come out a certain way, if I would make this matrix, and as I said yesterday, it's not a proper thing because these things in the first row here are actually vectors. And so this doesn't technically make any sense, but if we ignore the fact that it doesn't make any sense and treat it as if these 3 things are numbers temporarily, if I would expand this determinant by the first row, then what I would have when I do this business up here, but this would be I here. And that will give me the first component of the 3 things. And if you look at these 2 right here, what you see is A23, A, so on. If these are changed, this would be A2 and this would be B3. And that's what you have right here. In other words, changing from double subscripts to A and B with single subscripts, this right here is the same as this right here. Now, this one is not the same as this one, but it's the same as if you turn these 2 around. In other words, the definition for cross product, if you look at what I have my finger on here, and if you look at what I have my finger on here, this would be A2, A3, B2, sorry. I guess this would be A2, A3, B2. Just a second here. I'll put on my glasses because I have a shadow here. This would be A3 and B3, A3, B3. And if you look here, so if I multiply these together, this would be A2, B3. I'm sorry, I'm trying to, did I write this wrong earlier? What's supposed to come out is this right here and this right here is supposed to be the same. Now, did I write the thing wrong or am I just kind of screwed up here? So when I do this, I have 2, 1 and 2, 3. All right, this becomes B, A2, A3, B2. I'm sorry. This is A1. That's where I'm talking wrong. This is A1 and this is A3. So this should be A1 and A3, and that's why you will see these 2 numbers. But if you do this as A1 is over here. Now I've got my mind right. Okay. And by the way, I'm looking to see, I don't see anybody else wanting to come in at the moment. So if instead of these things, you write these things right here, if I do this one, it's this minus this, that's right here. Normally I would do minus this times these 2, but these 2 are A1, B3, A3, B1, and if you look, they're switched here. So in the definition of cross product that you actually, the actual definition, this right here takes into account the minus right here. Now, if you do it this way, you have to put the minus in. If you memorize it this way by the definition, then the minus is already incorporated in right here. But most people do this. Now, if you wish to do this the way I remember myself, and what I do myself may or may not be good for you guys, but if I just look at right here, that's 2, 3, if I look right here, that's 3, 1. And if I look right here, that's 1, 2. So what I remember, if I'm trying to write this down and look like I'm smart, is I'll remember A2, B3, I'll remember A3, B1, and I'll remember A1, B2, and then I know I switch them. A2, B3, and A3, B2, I just switch those two. A3, B1, A1, B3. So I remember these subscripts on these three, and then I can mentally write it down like I remember the whole thing. You may or may not want to do that. Most people do this thing right here. But what you have to remember is this is just a mnemonic device to help you. Okay. So if you guys got, and there's only 6 or 7 of you, if you got any questions about that, have I, after my original screw up, have I kind of made it understandable?
I think I get it.
Okay, now, this has nothing to do with 4x4 or 5x5 or 6x6, because the only cross product we do is 3 and 3. Now, however, of course, this can be done with 4x4, 5x5, 6x6, and I hope you'll see what I'm going to just say quickly. But if we would imagine that this would extend one over here and down one, so if I have a 4x4, then the way you do it to expand it, it's the same idea. You take the A11 and then below it, you'd have a 3x3 matrix. And so it'd be A11 times the determinant of the 3x3 matrix that would occur here, because I'd have another row and column, minus this number. And then you wipe out this row, which would have 4 things, and this column, which would have 4 things, and you copy down the 3x3 that's left over. And so instead of having 3 2x2, you'll have 4 3x3s. If I had 10 rows and 10 columns, the determinant of that would first be 10 9x9 determinants. Each of the 9x9 would be 9 8x8 determinants, and so forth. And that's really a mess. And by the way, just for your information, determinants on a computer are, you want to avoid ever putting a determinant on a computer. What people think is a computer can do 100,000 operations in a 1/10 of a second or something. And so even though humanly 3x3 is okay, but 10x10 is terrible, you put 10x10 things on the computer, it will get an answer in a 1,000th of a second, but it won't be correct. Doing determinants, and the reason is determinants make mistakes whenever you're subtracting. Big mistakes sometimes. And in every one of these things we do, there's a minus. And so what you're doing in all these operations on a computer is you're doing thousands and thousands of subtractions, and that's where error comes in. And that's a very much oversimplification, but you don't, just because the machine can do 10,000 rows and 10,000 columns in a second, if it took a determinant, the number may have nothing to do with the correct answer. Anyway, that is a discussion we might have some other time. Third thing I wanted to show you here is, if I think of this now as 3 rows, so A is going to, are 3 things, B is 3 things, and C is 3 things. Okay, so if I want to take a regular determinant, and that would be the same as up here, except now I'm calling the first row A, the second row B, and the third row C down. Okay, so we already know how to do it. And what you'll notice here, if I call these things A, B, and C, is A occurs 3 times right here. And this would be B and C, B and C, and B and C, because these are all 2 or 3s, every one. So it all has to do, when you do the first row, when you're doing the other 3 determinants, they're all in the second and third row. So we can actually write, and by the way, what are these 3 things? The 3 determinants, they're the cross product. So we can actually write the determinant of the original as the dot product between A and B cross C. If you look, I can make a dot product. What's a dot product again? You take the vectors and multiply the first things together, the second things together, and the third things together. So if I take A1, A2, A3 and multiply it times this thing right here, which would now be B's and C's, this is what I would get. Now, if I take an original determinant, suppose I turn rows 1 and 2 over. In other words, suppose I put row 2 where row 1 used to be and row 1 where row 2 used to be. What would happen to the determinant? Now, remember that if I expand the original determinant by the second row, I have to put minus to start. It would be minus this one, plus this one, and minus this one. If, on the other hand, I turn this over so that A21 would be up in the top spot, and I did that determinant, I would be starting out with plus it, plus, minus, plus. So what we prove, I'm hoping that I've explained it enough. If you interchange two rows of a matrix, the determinant changes sign. So if the original determinant was 3, and I turn row 1 and row 2 over, the new determinant will be minus 3. Now, if I make 2 row interchanges, meaning interchange twice, it will come back to the same. So if I would take row 1 and row 2 and switch them, and then take row 2 and row 3 and switch them, it turns out I would get the same original determinant. Now, why is that interesting? Because suppose now, and I hope you guys can, well, I did this right here. If I have BAC and do it, this would be this. And that turns out to be minus this. And so what happens, I didn't do it here because this is not supposed to be a class, it's supposed to be sort of helpful tutoring and stuff. We can play around with this stuff and get and determine facts that if we're in the book puts a black box around these things. We could determine properties of these determinants in terms of dot and cross products. Now, the thing I didn't do yet, but I will do now, suppose with all that information we've just now learned, suppose that I would have A, and C, I guess you can see that. Suppose I have the same thing here. Whatever the determinant of this would be, whatever it is, suppose it's 15. If I interchange 2 rows, I would then get minus 15, right? That's what we just said. But if the 2 rows are equal and I interchange, we have one person coming in. Mr. Day, can you hear me? So we just had one person come in. I hope you can hear me okay. I asked him to unmute, and so you can probably hear me, but he hasn't unmuted. Anyway, not worried about that. You can hear me. Okay. Yeah. Did you have trouble? I'm just curious. Did you have trouble finding it, or did you just get here?
I slept in a little bit.
Okay. No problem. I just wondering about, what's going on out there. Okay. We have been talking about, you can see on the screen here, we've been talking about determinants and stuff. So you've missed some stuff, but that's okay. I did record this and we'll make this available to anybody that wants to watch it later. Anyway, if I have 2 rows the same and I interchange them, that should put a minus on things. But you can't tell if I interchange them or not. And so what you get out of this, if I have 2 rows in a matrix that are the same, and I take the determinant of that, the answer will be 0. So If you have two or more rows equal, the determinant is 0. Now, why is that important to us? Because we can write a determinant of a 3 by 3 thing as a dot product. So what we're going to find out here is if I do this, this determinant will be 0, the number 0, or is it the vector 0? Well, a determinant gives you a number. Cross product gives you a vector, so we've got to keep those things straight. And dot product gives us a number. Anyway, so we'll have things like A dot A cross C is 0, for example. And if I change now and call this A and B, so if I just assume I have two things, so if I have here A, and B, then what I get out of this is A dot A cross B is 0. Now, that turns out to be very important for what we want to be talking about, because last week I told you guys, when I want to find the equation of a plane, I need to have a point and a normal vector. Okay. Well, what this shows right here is that this thing we just invented yesterday, the cross product, it is perpendicular to A. And if instead of AAB, I did BBA, that would also be 0. That would say that B is perpendicular to A cross B. So why do we develop section 4, the cross product? Because it creates a vector which is perpendicular to two vectors. If the two vectors make a plane, then the perpendicular vector makes the third dimension. So if I did this with I and J, I would get K. Okay. So if I had the X and Y axis, I could create the Z axis by doing the cross product. So cross products are very important because they give us perpendicular vectors to two vectors. And you've got to go into this a little bit with matrices and stuff to understand what instead of just being told. And that's why I was spending this time here this morning. So kind of as a review, we're going to have this vector thing called a cross product. It will only be something we do in 3 dimensions. And by the way, that's a little bit of a lie because we can do it in 2 dimensions, but most of the time we don't need to do it in 2 dimensions, so we don't talk about it. You can make a 3-dimensional thing, a 2-dimensional thing by putting 0 in the 3rd dimension. And then that puts everything on the floor, and then you can think of it as 2 dimensions. So we can do cross products in 2 dimensions, but normally we don't need to because we already are familiar with 2 dimensions. So when we talk about cross products, we are thinking without saying so that we're in 3 dimensions. So all the vectors have 3 components, and the cross product creates a perpendicular vector to the original 2 vectors if they are independent. Now, what if I would cross a vector A with itself? Then in this work here, I would have 2 rows the same. If I cross A with A, I'd have A here and I'd have A here. That's a determinant with 2 rows the same, and that's 0. So the determinant of a thing with itself is always 0. The determinant with 2 independent ones, and if I have 2 dependent vectors, they lie on the same line. And so one is just a multiple of the other. And so you'll still get 0. So when you have independence, that's when, and I'm going to take off the screen here. Now, if you have, I'm waving into myself into my own camera, but it doesn't show you guys. When I have independence, if this is any good thing, what I want is this 3rd vector coming out, which makes a perpendicular. When I have this perpendicular and a point, and either one of these vectors, the endpoints are going to be a point in the plane I'm interested in, The vectors themselves might not be in the plane, all right, but they're parallel to other vectors which are in the plane. Anyway, when I get a perpendicular and a point, either of these points, I can determine the equation of a plane. Okay, and that's like section 5 in the book. So I've been jumping around, as you know. I'm going to go back and now I got my finger pointing over. I'm going to go back here and show you one more piece of thing. So again, if we have two independent vectors, A and B, and I want a plane that passes through A and B. What I need is that one of the two things, I need a point. So I have too many points as far as what I need. I need 1 point. So if I take the point A, I can write x minus A1. So if A is A1, A2, A3, x minus A1, y minus B1, and z minus C1. That will give me this is like the equation of a line. If you remember, equation of a line is going to be y minus y1 equals m times x minus x1, something like that. We can rewrite that as m times x minus x1 minus, in this case, y minus y1 equals 0. I'm below the screen here. What I'm saying is it's a number times x minus x1 and a number times y minus y1. That's what a line is. I'm trying to do a plane. So I need a normal vector. So what we do is we take the cross product of A and B. If we call that C for a minute, and if I call that C1, C2, and C3, and by the way, we don't usually call it C, we usually call it N for normal. So if I make it N, and if I make it N1, N2, N3, this is what people, as I say, in the discovery mode, you might use C first, and then you think N sounds better. We put the first thing here, the second thing here, and the third thing here. This is the normal vector. And when we put it out in front, like a slope, put it out in front with the point, and this would be, this should have been A2, and this should have been A3. So this is the equation of a plane that passes through the point A1, A2, A3, and it has a normal vector N1, N2, N3. So suppose you see the following plane, equation in 3 variables. Immediately you know a normal vector is 3 minus 4 minus 7. And this particular one passes through the origin. This would be a plane that goes through the origin and as normal 3 minus 4 minus 7. You can make an arrow up that points in that direction. If I have 2 over here, that's going to be a plane that's normal, as a normal vector 3 minus 4 minus 7 is parallel to the other one. But you see, if I would multiply this stuff out here, then n times 1 times x, n2y, and n3z, that would be this right here. And this other stuff I could put to the other side, and that's where the 2 comes from. So if you see this, you can't tell what point they go through. But if you knew what point they go through, that would give you, if you multiplied n1, a1, and n2, a2, and n3, and add that up, that would be where the 2 comes from. So this one is parallel to one with 0. The one with 0 goes through the origin. Okay, is that sort of understandable? Anybody?
Yeah, I think so.
Okay, so we're going to talk more about that when the whole class is around. But what I thought so let me ask you, that's what I wanted to kind of just talk about, because I just didn't have time to get that much said yesterday. What we could look at is some WebAssign problems here, or any other things. Any questions you guys have, I'd be happy to try to answer. And you know, if you ask a really good question, I'll tell you we don't have time to answer it, and then I'll have to go home and try to figure it out myself. I'm home already, of course, but anyway, is looking at WebAssign a good idea, bad idea? What do you think?
We can look at WebAssign, I think.
Okay, anybody have any better idea?
WebAssign's fine by me.
I
Okay,
have a question about one of the WebAssign questions in section 1.
okay, you want to do the WebAssign first one? Is that okay? Because all right, let me share a screen. Go to WebAssign. Hopefully, I'm hoping that you get a screen now. We are actually at the moment, I got to remember which computer I'm on. We're actually at the moment, does that move your screen? No, I'm moving mine. That's this. I'll go back home here. All right, now I have the 5. Just a second. I've got on this particular computer, I've got the, that doesn't want to do that. Okay. You want to do section 1? Is that what you said a while ago? Let's go to
I
see.
just had a question on one of the problems.
Okay. Do you remember which? Now, as you guys all know, I think we haven't really talked much about it, but as I think you know, you get different answers for different people. When I look at this, and by the way, I cheat, you see, I've got answers. It tells me when you do this video that you should say false. You guys don't have that, but I do. So today you can see what the answer is, even if you don't know how to do it. Anyway, when you get to problems, these numbers in red here, they change. So every 2 of you who put your computers together and look at them, in problem 4 here are probably going to have different numbers right here. That's what the red numbers tell me. So we will do a problem like your question, but it may not be exactly your question. Okay. You remember which problem it was?
It was number 34.
Okay. And by the way, we need to keep track of the time because I'm liable to sit here all day with you guys. I need, yeah, okay. Number 34, find an equation of a sphere containing all surface points such that the distance is twice the, okay, so now, first of all, for you guys, whether or not I explain it very well here, because this looks like a problem I have to write some stuff down with, so I may have to go to the other screen a little while here. But if this were your problem, you might want to copy these numbers down. This is what you're supposed to get for this problem. And if you know what you're supposed to get for one problem, you might be able to change the numbers and get the right answer here. And that's independent of me. I'm just saying, this shows me what the answers ought to be, not why, but what. So, okay, find the equation of a sphere containing all surface points such that the distance from the surface to A is twice the distance from P. Okay, so P is going to be on the surface. I've got to try to digest this myself because I have not done it. P to A and P to B. Okay. Points. Yeah, well, first of all, I think this is a pretty good problem in the sense that I can't just tell you the answer offhand. And so we've got 2 points in the plane. And let's see, they're not parallel to each other. I mean, they're not, I don't know if they're parallel, but they do not have the same second or third or first coordinate or anything like that. So, okay. Now, I have no idea how to do this, so we're trying to discover, okay? If a point is on the surface of a sphere, now, let's suppose that we had worked on this and we got this answer. Just I want to use the answer here. In general, what we're trying to do is to find the center, which is this number, and this number. And this is the square of the distance of all points on the sphere from the center. So this number we're finding here is not going to be a point P. Point P is going to be at a distance from the center, from this point. And so how are we going to put together 2 points now? So what I would do here to start out is I would say, take a point P and measure the distance here. The distance would be the square root. We can do this on a piece of paper in a minute. The square root of XYZ. And by the way, I would prefer myself to say the point is X naught, Y naught, and Z naught instead of XYZ, because we're later going to say the set of all XYZ. And when the author has this, we're basically saying all surface points, but we're going to be doing this one at a time. So I would probably say, okay, let X naught, Y naught, Z naught be a surface point. Any surface point, I don't care which one, but I want a particular one. And then I'm going to measure the distance from here to here. So I would have X1 minus 1, X naught minus 1 squared plus Y naught minus 6 squared, and so on. I would have that. Now, I might also, just to avoid square roots temporarily, is square everything. Okay. And what I don't know is what the distance is. So I would probably call that D1. As I say, I'm discovering, I'm making up what I'm going to do here. I would probably call this D1. That's because I don't know what the distance is, except over here it says it's twice the distance from here. Okay, so I need to compute the distance from X naught, Y naught, Z naught to here. That's another sum of square roots of stuff. I mean, sum of squares and stuff. And that would be equal to, now I said, if this is the distance here and it's twice this distance, maybe I ought to make D2 the distance D, and then this would be 2D. Okay, so this would be D squared and so forth. So it looks to me like what I've got to do is go back to the screen and paper and work on this. Now, what we'll do here, we don't know what this distance is, but I know that one distance is twice the other distance. So I can get rid of distance. And so if I replace the distance, that sum of squares of one thing is going to be twice the sum of squares of another. And so I'm going to get an equation with sums of squares in it. Now, so as I said, let me copy this. The best way I know to do it right here is let me copy down the statement here, and then I'll show you the other screen. Anybody? So how am I doing? In other words, you guys see what I'm trying to do? If you don't,
Maybe.
I'll try to make it better. See, that, you know, this is a test for me. You understand? You're springing this on me and I got to answer it or I'll look like an idiot. And so it's a test and I may fail the test. That's what happens. Okay, so I'm also going to cheat. I'm going to copy down the answers so when we get the answer, we'll know. And the reason is I've got to get off this screen to be able to show you the other screen. And so, okay, writing what I wrote the equation down. I can see that, and yeah, I don't need to have the radius and the other one because they are obvious to me from the first answer. So let me get rid of this. And by the way, I'm not trying to run out of time, but it's 17 after. Let me go to the other screen quickly. Share that. Okay, so what I wrote down a second ago is this. This is the answer. What I would do, as I say, is compute -1 minus x naught squared plus 6 minus y naught squared plus 2 minus Z naught squared, and that I call D1. And I would, if you can, because I'm trying to do this fast now, 6 minus X naught squared plus 3 minus Y naught squared plus minus 3 minus Z naught squared. That was D2, but I believe we said that this distance was twice this distance, right? And so if I would multiply all of these by 2, then I would get D1. And if I would set these two things equal, so in my time here, I want to set these two things equal. I need to multiply stuff out. When I multiply stuff out, I will get something in X naught, Y naught, and Z naught. Okay. But remember, that was a point on the surface of, if I remember it right, we took P naught was a point on the surface of the sphere. So I'm going to get an equation which is going to be like a sphere, but it's a sphere with P on the surface, not in the center. So that I will have to, I mean, my problem is it's now 19 after. That I've got to figure out. So what I will do with you guys here seriously is I will write this one out, and if we're in class tomorrow, I'll hand it out to you. If we are on Zoom, I will show you the answer. I'm going to stop the recording here.